as Jade mentioned, I'm the first hard rock talk you guys have gotten here, so it's a privilege, and hopefully I won't bore too many uh, paleontologists with my talk about rocks. Uh, so yeah, as Jade said, I'm talking about water and specifically how it moves through the crust by hitching a ride with crustal melts. So okay, yeah, there we go. Yeah, I am. That's me. As you can see, I'm a PhD student at the University of Waterloo, as Jade mentioned, and I study the metamorphic rocks in Ontario, and like to learn about how fluids and melts in the crust interact. So let's get into it. First of all, we have to talk about why water in the crust is important, why we care about it as geologists. Now, the first and most obvious reason is it's required for life on Earth. It's probably the most important chemical for Earth life, and without water, life as we know it wouldn't exist. Although whether or not water is necessary for life is a topic that I will not get into today. It's also responsible for the genesis of like a lot of different types of ore deposits, things like copper and gold and silver and cobalt, all sorts of fun and interesting and critical metals, all that fun stuff that people care about. Water is pretty essential to a lot of those. It's also might be a necessary component for subduction. Did I have, where's my laser pointer? Oh dear. Okay, well, my laser pointer is not working for some reason. That's okay. Oh, here we go. No, that's not it. Apologies. Okay, whatever. So it might be necessary for subduction since water is lost from the subducting slab, and it metasomatizes the mantle above it, and that might be something that's necessary to keep subduction moving through the crust. It's also responsible for melting rock under specific circumstances. So that's kind of the side of things that I'm focusing on in this talk is how water melts rock and how melt transports water and how all these processes play in together. So that's an important thing to talk about because that's how we get a lot of volcanoes, particularly the particularly destructive volcanoes tend to be from magmas that have a lot of water in them. It's also how new continental crust is formed from melting in the deep crust, and also certain types of ore deposits like lithium is the hot topic today. Water might play an important role in those. So rocks melt for more reasons than just adding water. The most common reason crustal rocks melt is just because they got hot. And so water only melts rocks in very specific places. So let's talk about where that actually happens. Most significant one I already sort of talked about is subduction zones. So again, where water dehydrates from the slab, it will move into the mantle and melt the mantle wedge above it, and that's where we get island arcs, continental arcs, and all that. This is probably where the greatest amount of fluid flux melting occurs. And when we get into the crust, it starts to get a bit more complicated. So if rocks are hot enough, but not quite hot enough to melt, water can reduce the melting temperature. And where water flows, for example, along fractures, we can end up getting melt around these fractures. These can be pretty short-lived, though, because the water in the fracture is pretty quickly replaced by melt, removing that pathway for water to flow through. In a similar sort of way, we can get fluids along shear zones, melting rocks in and around those shear zones. And that can be a bit more extensive than just fractures. I mean, fractures can show up as well and play into that, but the shear zone network can provide multiple different pathways for fluids and fluid rock interaction and melts and melt transport that don't necessarily interfere with each other as much. So you can get much larger regions of melting, but these are still quite localized. Shear zones can be relatively small, especially compared to, for example, subduction zones or regionally extensive melting from heat. A more extensive scenario is when a hot slab is thrusted on top of a cold slab. So this goes on top, that goes down here, and the water and other volatiles will be lost to the hot slab, and that's where you can end up getting melting because it heats up and the melting temperature is reduced with the water, and you can get some fairly large extents of melting. And finally, one of the most significant occurrences that we see throughout the world is when water is lost from other melts. So fluid flux melting from other melts, which is maybe a bit counterintuitive almost. Can melt transports water and makes more melt? How exactly does that work? Well, so we have to understand that water partitions very strongly into melt. So this phase diagram on the right here shows that when melting occurs at low temperatures, for example, up here, water content, these red lines, can be quite high in the melt. So we're like right here, it's 11% by weight of water in the melt. And so when that water-rich melt forms, it can be transported. It might move through the crust during decompression. So it'll reduce pressure, and then the water will be exsolved as little bubbles maybe, and gradually as things crystallize, it'll be released into the surrounding rock as fluids. Alternatively, if you have fluid loss as the rock crystallizes, and it'll at constant pressure, the fluid will just exsolve from the melt as an additional phase, and that can be lost. That can be lost to the surrounding rock as well. So, strange. Okay. So this is kind of the more classical model of how melt transports water. A magma body might move through the crust, sit somewhere, crystallize, exsolve its water, and that water will be cause more melting around it in the aureole, in this sort of region around it. And that's has been generally thought to be significant, but not necessarily something where we see regionally extensive melting in the crust. An alternate model that's been proposed, or not necessarily alternate, but additional model for melting is one that doesn't necessarily involve any crystallization of the melt. So this situation where we have water-saturated melt being moved through the crust and that water being in the melt being lost to the surrounding rock around it just through diffusion. And that water being lost through diffusion causes melting in the crust around it. So this requires no actual fluid being formed, no exsolution. It doesn't even necessarily need any fluid moving in the any free fluid in the crust at all. It just needs a water-rich melt. So there's some good evidence that this happens, but main question is where does it happen and how, and is it that significant? So I'm going to move to a case study. This is what my work has been focused on primarily in the Grenville province. So that's those of you who aren't familiar, ancient 1 billion-year-old mountain belt that extends from contiguously from Ontario to Labrador, but there's a lot more little outcrops throughout down to like Texas and parts of Mexico and Newfoundland, and I believe even up to like some parts in like Scandinavia and stuff. But it's contiguous from basically on the Georgian Bay, the Lake Huron in Ontario, all the way to the coast of Labrador. And I'm focused specifically on this area, this dashed box here. And for reference, this is Toronto. It's where I am currently. And it's pretty accessible rocks for us. So it's a good little case study. And the specific region I'm looking at is a region of rocks that have been metamorphosed around 1100 to 1000 million years, 1090 to 1020 to be specific. And it's a region called the Muskoka domain. So that's this sort of purplish, maybe lilac colored region here. So zoomed in, take that box and zoom it in. And this is a region that has had quite extensive evidence of melting. So there's a lot of migmatites in this region, and it's fairly got a fairly large lateral extent. And if you look at the cross section, it's rather thin. So it's maybe like 5 kilometers thick. Its true thickness. And it's this sort of thin wedge between stuff that is generally, we've got paratoctonous stuff over here, and then there's alloctonous stuff. This is all alloctonous stuff to some paratoctonous, and this is more alloctonous stuff that's coming from more distal regions. These are so we're looking at a specific, this Muskoka domain is a specific alloctonous domain that's been kind of wedged between two unrelated terrains. So throughout this region, we have a lot of migmatites. So partially the relict partially molten rocks and they have high volumes of leucosome. So in this picture, it's this pinkish rock that's all leucosome. So this is the relict melt that's been crystallized in the rock, and we can see all sorts of different types of expressions of this leucosome. Or these migmatites with variable amounts of leucosome, but generally quite a lot of leucosome, and a lot of these kind of, you might see little dark minerals, these little black dots. It's a lot of amphibole. So we can see maybe more clearly here if we zoom in. There's some big black crystals These are a lot of amphibole, some biotite, a lot of water hydrous minerals. So here's another example of a maybe not as clear the leucosome, the boundary between the leucosome and the host rock. But if we zoom in, we can see nice big amphibole crystals. And so this is not super typical of migmatites. We don't usually see large amphibole crystals forming in the leucosome. And so the hypothesis for how we get these large amounts of melt at temperatures that we don't necessarily expect large amounts of melt, with lots of amphibole and some biotite present. We have the hypothesis is that this was generated in the Muskoka domain by the addition of water. But the main question is essentially, how did that water get here? We're talking about, again, this sort of thin wedge of crustal rock in the middle of the crust. There's not necessarily a clear source for the water. And then the second question is, how much water is actually needed to generate this amount of melt and these amphiboles? So I'm going to kind of start with this question. How did the water get there? So coming back to the map, we have these little triangles are my sample locations. We can number them. Some key outcrops that have some interesting features that I'm going to show to you guys. So at outcrop 1, we see this interesting example where we have a pegmatite, this guy, intruding into this high grade, relatively dry rock here with lots of garnet and clinopyroxene. And on the margins of this pegmatite, between this thing labeled B, the margins here, we have this reaction halo where we've got, when we zoom in, we can see a lot of this sort of pinkish rock, little leucosomes by the looks of it, and big amphibole crystals as well. And then also like a lot of smaller, oh dear, went too far. Sorry about that. A lot of smaller kind of dark specks, which are also amphibole crystals. So there's a lot of amphibole and a lot of pink feldspathic material that appear in lenses that look like leucosomes. So it looks almost like there is partial melting occurring in this B region here, this reaction halo, and the generation of amphibole. And when we compare this to the migmatites that I showed you earlier that just we see throughout the region, it looks very similar. It's got these large amphibole crystals again in the kind of bigger leucosomes with some coarser grained mixture of amphibole and kind of feldspathic, like feldspar and plagioclase around it. And this isn't the only place we see this. We see it kind of here as well at outcrop 2. This is a bit more deformed. We can see, again, the large amphibole crystals with sort of pink leucosome. This is maybe a bit more layered, a bit more foliated, possibly as a result of the deformation. And we see these big amphibole crystals in the pegmatites themselves. And we can see it here as well, outcrop 3. This is maybe a less extreme example, bit smaller scale, not as big amphibole crystals. If we zoom in, we can kind of see it's a subtle difference between the host rock and the reaction selvage. Yeah, so there's lots of interesting examples of this. Over here as well, this is a much bigger example. So this is outcrop 4. Oh, that shouldn't be there. Okay, sorry. At outcrop 4, we get these really big halos or selvages between the pegmatite and the host rock. And I don't know if the color shows up as well on your screen, but you might be able to see a clear sort of color difference between Unit A and Unit B, where we have a lot more clinopyroxene and garnet in Unit A, and a lot more leucosome and amphibole in Unit B. And we can zoom into that Unit B even further, and we can see this clear kind of leucosome with these big amphibole crystals. And that looks very similar to, again, the migmatites that we see throughout the region. So there's a lot of evidence in this region for fluid flux melting that has amphibole and biotite as byproducts of this melting. And if we look at, so if we zoom in to the rocks, and specifically of this outcrop here, if we look at the host, we can see pretty clearly some high grade dry mineral assemblages. There's garnet, there's orthopyroxene, and clinopyroxene. There's a bit of amphibole as well, but generally these are like these dry, high temperature mineral assemblages that we expect to see in high temperature rocks with not a lot of water. And when we look at the reaction halo, the selvage, we see a very stark difference. We see a lot more amphibole. We see a lot more biotite with these kind of wormy textures. And we do see a bit of garnet, but the garnet's starting to have this more, we do a comparison, got these nice straight edges here. And if we look here, there's a lot more kind of rough edges, kind of eaten away, like it's being resorbed. It's getting consumed by the melting reaction. And then when we get right up to the margin of the pegmatite, there's very little garnet and a lot more biotite. It's almost like this is just a hydrous melt that's been crystallized. So we get this very clear association of melt assemblages and leucosome around these pegmatites, and it creates a clear image of these pegmatites as conduits for water, specifically as conduits for hydrous melt. So since we're talking about a relatively high grade terrain, there's the units below the domain we're looking at. So that would be this represented in this section here. There's a lot of evidence for melting in those things below, and when that just normal melting from heat and from the breakdown of hydrous minerals, that water will go into the melt, and so we get a lot of melting here. There might be a bit of melting in the Muskoka domain, so that's this guy here. We'll call that MD. This is we called the Algonquin domain. The stuff below it, but there's a lot more melting happening because it's hotter, and that melt will be quite hydrous, and it'll collect, and it gets transported up through the crust to lower depths into the Muskoka domain. And that hydrous melt will lose H2O via diffusion in those pegmatites. So this is an example of one of the pegmatites that we see. And so that water is lost to the host rock and will induce melting in or around the pegmatite. And then finally, enough melt is made that it'll collect and move and start to move through the crust again. propagating further up. So that kind of explains that. That's sort of our model for the more smaller scale pegmatites and their associated reaction halos. But these are pretty rare structures, and it doesn't really explain how we get. So there's a big question of how do we get from this to the extensive gneisses and migmatites that we see throughout the region with large volumes of leucosome and amphibole porphyroblasts and crystals throughout the region. So the model that we kind of working with is basically we start off with a relatively undeformed rock where these pegmatites intrude into the host rock and they lose water and they cause the melting. And as that melting occurs, the rock gets weaker, and we're talking about a mountain belt. This is during orogenesis, so there's a lot of stress. And as this rock is stressed and it undergoes deformation, it starts to get more deformed, and we start to get these kind of more patchy migmatites that kind of have signs of deformation, but maybe they're less deformed, and there's not as clear associations with the melt and the host rock, and where's the host rock and where's the reaction selvage. And this gets weaker and deformation progresses even further until eventually we end up with something like this, these dramatic gneisses, these strung out migmatites. These are this is kind of like the most deformed, what we think is the most deformed expression of these fluid flux melting structures as a result of intruding pegmatites, to the extent where we really don't have any really great association between what the fluid conduit was, what's the new melt that's being generated, and what the original host rock is. In migmatites, there will be variable layers where some layers will appear to be more, there'll be the leucosome, which is the stuff that's more melt dominated, or that's more dominated by former melt. And then there's the melanosome, which is the much darker stuff. That's the rock where the melt has left, and then you just have the restite left behind. So that would be like maybe these darker things here. And then there's the stuff in between, the mesosome, which is more expected to be what the original rock looked like. That's the kind of grayer stuff here. So we can kind of compare then, take the mesosomes and the leucosomes and compare them to the host rocks that we see near the pegmatites. And, oh, that's not a very nice resolution. Anyways, we can see when we compare the compositions of these rocks, so the host rocks in the sort of yellow compared to the mesosomes in the dark blue, the reaction the selvages, the lighter blue, and then the leucosomes and the pegmatites. So we can see the mesosomes and the hosts have a somewhat similar composition over here. There are a few outliers, of course, but they're mostly concentrated over here. So fairly similar composition between mesosomes and the unmelted host rocks. And then we can kind of see, as we move to look at the pegmatites and the leucosome, they're kind of on a similar trend away from the host rocks. So they're kind of they get to be more alkali rich and less iron rich in the same direction, and they start to get similar compositions. So we start to see more similar compositions of the leucosomes and the pegmatites. And if we look at the reaction selvages, they kind of move in the opposite direction up here. I don't have the melanosomes because there weren't that many compositions to look at. But it's the selvages kind of move in the opposite direction of the pegmatites and the leucosomes. And that kind of makes sense because you're removing the melt, and the selvages are the sort of things that remain. So, okay, so what's our tectonic model look like for this region then? How do we get the domain that we see that has this large, regionally extensive fluid flux melting? Well, the sort of simple kind of block model that we have is we got the Muskoka domain, this block here, above the underlying stuff, the Algonquin domain. So Muskoka, and we'll call this Algonquin. And so this is being thrusted on top of the lower stuff, and the lower stuff is getting brought down to higher temperatures and greater depths, and it'll eventually go down below the solidus, even with low amounts of water. And this will just be normal melting as a result of heat and hydrate breakdown. So muscovite and biotite will break down and create melt. And so that melt will collect, and it'll move up through the crust into the overlying slab, and it'll lose water into the surrounding rock. And then that causes more melting in that'll cause the fluid flux melting that we see in the overlying slab. And that stuff, since it's being thrusted, it's being dragged up, it gets moved continuously over top the source material. So we end up with this continuous cycle, essentially, of rock being added underneath and melting, and that melting rock moving up above and releasing water and causing melting in the overlying slab, and that molten rock moving, getting pulled up through the crust, uplifted, possibly exhumed and exposed, possibly eventually brought to the surface. So this is a continuous cycle of melting and transport and water transport through the crust up to higher levels towards the surface. So it's a mid-crustal water cycle in a way, and as long as this thrusting continues, we can have this process happening continuously throughout the evolution of the orogen. And this actually this lines up pretty well with some of the models for the tectonic models for the local region. So where does that leave us at the end? So what's what can we conclude from all this? So first of all, melt is an efficient way to transport water through the crust, and we can end up with large volume of melt that can be produced as H2O is lost to the host rock. And finally, one of the more interesting conclusions is that we can see H2O flux melting occurring on a regional scale, and possibly affecting the development and tectonics of large orogens like the Grenville province. There's still standing questions I'm kind of trying to answer about how much water exactly is being transferred, and how much do we need to happen for this process to happen. But that will have to be a question answered another day. Anyways, thank you for listening, and I hope you all learned something.